So first, I'm going to walk you through kind of the entire process, starting from training the model, just to train a simple model that actually runs on data and actually predicts something. Then we're going to simulate the deployment when we will have a production data set that we have no access to, not during training, not during evaluation, not during testing, and it just comes after, and we see what happens with it. We'll be able to see that there is some issues to performance with it, and then we'll go into the main part of the tutorial, which is how to actually detect data drift. So let's start with importing the YAML and just a few things to load the data and things like pandas. We're going to load the data. It is a data set that's available on OpenML organization. It's a very nice nonprofit organization that has a lot of very cool real-life data sets. So very highly recommended that you give it a go. Then we are loading the data, and what we see here is that we have few features about when certain thing happened, and what we're actually trying to figure out is how many people signed up for bike sharing application or actually shared a bike during given season, day. I think it's day. Oh no, it's hour, during given hour. And we're going to just quickly pre-process the data here. So first thing, we're going to define what's our target, which is the count. And then we'll have to drop some features. First of all, we have to drop the casual and registered features because they actually have very bad memory leak that they just add up to our count. So it wouldn't really make sense to build a model if these two features actually just give us the answer. And because I'm really lazy, I'm just going to also drop everything that is not a number already, which is weather and season. And I'm additionally going to drop the count because that is just the target. So let's do that. Then we're going to split the data, and we're going to split the data in our training, testing, and our production. Because we're not going to optimize on the hyperparameters, there's no need to really do anything with the validation set. So I'm just going to split the data, and I'm going to use time series split here. So we're going to start with the things that happened earlier, and then we're going to test on things that happen later. And then the last part of the data set is going to be reserved for production. And now we just simply train the model with default parameters. We're training LGBM regressor, the most standard thing you can potentially come up with. And we're training that on trained data. We're going to make predictions, and we're going to predict on training, testing, and production. So kind of simulating that we actually have a separate set that we didn't see at all. And then we need to prepare the data for NaNML. This is kind of where the NaNML part starts. So what we're going to do first is we need to define our reference data set. And again, as I already mentioned a few times, perfect data set for that is the test data set. So that is exactly what we're going to do. We're going to take the test predictions, test features, and test ground truth. And we define it as our reference data set. And then to analyze, we could analyze just specific part of the data when something has gone wrong, but why not analyze everything to have a bit fuller view since the data set is not that big. So here for the analysis, we're going to take our production data, the features and the predictions for the time being, assuming we don't have very easy access to ground truth. But right after when we fit our performance calculator, let's just assume we do have access to that. We could also estimate our performance without access to ground truth, but just to show you that there are really issues with performance. It's not that we're just estimating and hallucinating issues. There's actual issues. If we try to compute our performance using MSE or MAE, we will actually see that there is issues with our model. So we're going to add targets to our analysis, and then we're going to just calculate the performance, taking the performance calculator and calculating the performance, obviously on analysis with targets. So let me just run it, and we all see here that during testing, everything was fine. So we felt quite confident that we can deploy the model, even though it kind of climbed up at the end, but probably when we train the model, we just look at the total or average performance in our test data set. We don't try to segment in time or do other things like that. So it probably looked fine. But once we deploy it, we'll see that there's huge spikes both with MSE and MAE. So whatever method we use, we see that there's some issues with it. Now, what might have happened? Let's start with the univariate drift detection. So again, I will make sure just here that our predictions are treated as categorical to make sure that we get the right kind of plot. And then our columns that we want to look at, I'm just going to take all the model features and that the model has looked at, just to see what is going on step by step, feature by feature. And then, as already mentioned here, we're going to take our column names as column names, and we're going to compute our recommended metric or method, which is junction channel distance. And what do we do then? We will use our univariate drift calculator to fit on reference. And the only thing that it's actually fitting is that it's taking the reference data, and for some methods, it's going to bin them, so you don't have to store the entire thing when you compare it with your analysis data. So if you want to just fit your calculator, let's say you have a few terabytes or a few hundreds of terabytes of data, you can still fit the model or your calculator, and then you'll be able to store just the histograms of the data, which makes storage possible, easy, and then you can easily compare it with your analysis data, which normally will be much smaller. So we'll fit it, and then we'll calculate the results for the junction channel distance on our analysis data, and we'll display the results, turning that into data frame. So one way of viewing results is just to manually go over them as a data frame. You can take the data frame and you can do whatever you want with it that you would be able to do just with a typical pandas data frame. So what you see here is that we have our indices. We're going to just split our data by index for our analysis data and our production data. Oh, sorry, for our reference data and our analysis data. So in other words, test and production. And then we're going to have kind of a funny multi-index thing when for every feature we have a potential list of methods, because we can select more than just one method, as you can see here. And we will see what is the threshold for which we consider that something has gone wrong, and what is the value of an actual metric, and what is potentially lower threshold, as some methods might have a lower threshold as well. And whether we see that as something problematic, so whether there's alert is true. So you could just take it and plug it, for example, in your retraining pipeline to automatically retrain if you see that specific things are drifting too much and you want to retrain, and see whether automatic retraining actually fixes the model. So there is some potential for nice automation here. But the other way of viewing the results is just with plots, and the way we do it is we'll take the results, we'll just say dot plot, and the thing we actually want to view is the drift. So we're gonna say that the kind here is drift, and we just show it just like we would show any normal matplotlib or plotted figure. And again, exactly what we saw before. And there's few weird things going on that hopefully help us build understanding of why performance is decreased. So first of all, year is always drifting. In every single chunk of our data, year is drifting, which actually makes sense because it's always monotonically increasing. So it's never going to be the same as the distribution of our entire test set, which already probably gives us some idea of the mistakes we might have made or have made during during training and preparation of this algorithm or of this model. Then we see the same thing happens for a month, is that it always drifts. But in that case, it might make sense because we're looking at kind of a univariate distribution if this data lasts more than a year. But for every period in our data, every chunk, we probably had only 1 or 2 months. So it's drifting. It's fine that it's drifting. It's just cyclical data. But it's good to see that this is actually happening. Then we have hour, which is equally distributed. There's no changes there. We have whether there's holidays or not. And we see that there are probably, again, months when we see a lot of holidays. And it might actually mean that there is something wrong with our models when there's a lot of holidays, but we're not sure yet. For weekday, we see a very weird thing going on, is that this data for testing was probably in some way ordered, but for production, this data was completely not ordered and it's completely random, and it looks exactly as the data for the entire test set. But again, none of those actually exceeds our drift. So we're sure that the distribution of our weekday has not changed significantly, but it's something to look into when you develop your model. And if you see something like that, then probably you should think about whether this is actually something that you're happy with. And then for working day, no changes. It all looks very good. It all stays below the threshold. For the temperature, we see that there are significant changes, and especially there is a big jump here. So again, we have cyclical data, and we already start to build the intuition that we probably build our models to take into account cycles in an incorrect way. And there's something wrong going on when we have different parts of a year-long cycles. Cloud temperature, the same thing. Humidity, kind of similar thing. Wind speed, similar thing. So there is something going on with cycles. We already managed to figure out that we probably did not really think through how we're gonna treat temporal data when we develop that model. So temporal data, then let's continue our investigation, and instead of just doing normal multivariate detection, let's do multivariate detection of all features to get a general view of what is the drift for the entire data set. But also let's drop two things that we already know are drifting and have a recent drift, and there's probably issues with those. So year and a month. So I'm going to run that as well. And then we're going to initialize our data reconstruction drift calculator, so our multivariate drift detection calculator, just putting all column names for the time being. So not those, but the ones we defined earlier. Then we're going to fit it on reference. So we're going to train our PCA model on reference that's going to learn how the data looks like. And then we are going to calculate. So we're going to run it through the trained PCA on our analysis data. And what we see, there is huge increase in the error. So definitely there is drift, and this drift probably actually is one of the causes for drop in performance. But now let's drop our year and month. So let's do the same thing. Let's fit it again without a year and a month. And what happens? You see that there is actually no drift. So that, what does it tell us? Is that all important drift and all important changes in the model, all covariance shift in the model is really captured in the month and the year columns. And we shouldn't have trained our model, and especially we should not have trained a gradient boosting model on a year, because maybe there is a trend in our application. Maybe more and more people start sharing bikes using our application, which is something that you would hope for as a business. But we did not take that into account. And our gradient boosting model just assumed that the higher the year, the more people on average are going to actually share the bikes, but it just took the cutoff on the last data it shows, and it failed to extrapolate this trend further, because it's not something that tree-based models can easily do. And the drop in performance is due to us taking our year and month into consideration here. So this is something that we'll have to think about now as data scientists, and try to kind of redevelop the model in a way that doesn't take year and month into account in such a simplistic way. And that's it. We know what happened. We know why it went wrong. And then we can start working on resolution, which in that case would be full model redevelopment, because retraining won't help here. We know that the model would fail later on when we see the next year. And that is it. That is the end of the tutorial.